Hi everyone. Welcome back to Coding Fab. In today's lesson, we're going to dive into Twitter sentiment analysis, a powerful natural language processing project where we use machine learning to classify whether tweets are positive, negative, or neutral. You'll learn how to clean and pre-process text data, convert it into numerical form, train a classification model, and evaluate how well it performs on unseen data. If you're new to text analysis or working with real-world datasets, don't worry. I'll walk you through each step clearly and explain the key concepts along the way. This project is a great way to sharpen your skills and see how machine learning can be applied to everyday social media content. All right, let's get started. 1. Understanding the project. This project is a classification task and a classic example of natural language processing, NLP, which focuses on enabling machines to understand and interpret human language. The main objective here is to predict the sentiment expressed in tweets, whether they are positive, negative, or neutral like this. The dataset used is the Twitter sentiment dataset from Kaggle, which contains thousands of tweets labeled with corresponding sentiments. The data type is text, meaning each input is a piece of unstructured natural language that needs to be converted into numerical form before modeling. This task is framed as a multi-class classification problem, since tweets can belong to more than 2 sentiment categories. The primary algorithm used is logistic regression, a strong baseline model for text classification. It's effective, easy to interpret, and works well with feature vectors generated from textual data. To evaluate model performance, we use standard classification metrics: accuracy to measure overall prediction correctness, precision, recall, and F1 score to evaluate performance on individual sentiment classes, especially important if the dataset is imbalanced. This NLP project is developed using Jupyter Notebook, and the following tools are used: Pandas for data loading and manipulation, scikit-learn for modeling and evaluation. TF-IDF vectorizer means term frequency inverse document frequency. This is for converting text data into numerical feature vectors. And we'll follow the basic machine learning workflow as shown in the upper right. Okay, let's dive in. 2. Data collection. Let's download the dataset into your system. To collect the data, visit Kaggle. Go to the dataset section and search for Twitter sentiment analysis. Then click the download button to get the dataset. Once you download the data, you'll see 2 files. This time we will use only the training CSV file. Once you open the file, you'll see these features and the target label. It does not include column headers, which means we need to assign them manually when loading the data. The target label is sentiment, whether the user is positive, negative, or neutral. 3. Loading the data. The goal of this step is to import the dataset into our Python environment so we can work with it using data analysis tools. Since the dataset has no column headers, we also need to assign meaningful column names manually. To assign column names, you can write like this. Then you'll see the data table like this. Let's move on to the next step. 4. Exploring the data. The goal of exploring the data is to understand its structure, size, and quality. We want to identify patterns, check for any unusual values, and get a sense like how many tweets there are, what the sentiment distribution looks like, if there are missing values or duplicates, the average length of tweets, examples of each sentiment, and so on. Let's explore some data. For example, the info method tells us about the structure and completeness of the dataset. The dataset contains 74,681 rows and 4 columns. The ID column is an integer and has no missing values. The topic, sentiment, and text columns are of type object. The text column has 73,995 non-null entries, meaning some of them are missing text. From the sentiment value counts, This shows the number of tweets labeled with each sentiment. Negative 22,542 tweets, positive 20,831 tweets, neutral 18,318 tweets, and irrelevant 12,990 tweets. According to the Kaggle description, irrelevant should not be treated as a fourth class. Instead, we should relabel all irrelevant entries as neutral later, so the dataset only has 3 valid classes. IsNullSum shows the number of missing values in each column. Only the text column has missing values, 686 rows. All other columns are complete. We'll likely need to remove these rows in the cleaning step since a tweet without text cannot be analyzed for sentiment. Duplicated sum reveals that 2,700 rows are exact duplicates. These duplicates should be removed to avoid biasing the model with repeated examples. Now we briefly understand the dataset. Let's move on to the next step. 5. Cleaning. The goal of data cleaning is to remove or fix data that is incomplete, duplicated, or not useful. This ensures that the dataset is clean and reliable before feeding it into a machine learning model. From the exploration step, we discovered that the dataset contains 3 key issues. Missing values in the text column, specifically 686 tweets without any content. Duplicate rows, a total of 2,700 rows are exact duplicates. Irrelevant sentiment labels. 12,990 tweets are labeled as irrelevant, which are not valid according to the official definition. To clean the data, first drop all rows where the tweet text is missing with drop-in-a method, since tweets with no content cannot be used for sentiment analysis. Next, we remove all duplicate rows with drop duplicate method to ensure that the model does not see repeated data, which could introduce bias. Finally, based on the Kaggle description, we replace all irrelevant sentiment labels with neutral using the replace method. After cleaning, all rows now contain valid tweet text. All duplicates are removed. Sentiment labels are now standardized to 3 classes only: positive, negative, and neutral. This prepares the dataset for the next step, preprocessing, where we will transform the text data into a format suitable for machine learning models. Another essential part of the cleaning step is cleaning the text, especially for NLP tasks like sentiment analysis. The goal is to fix unclean text such as URLs, hashtags, and symbols. Let's create a function called cleanText to normalize and clean the raw tweet content. The function first checks whether the input text is a valid string using the isInstance method. If not, it returns an empty string to avoid errors when processing non-text data. The lower method transforms all characters to lowercase. This ensures that words are treated the same, reducing unnecessary variation. Other methods use regular expressions. The first one is to remove URLs. URLs typically don't carry sentiment and can be distracting. The next one is to remove mentions such as @username. These don't affect the sentiment directly and can be treated as noise. The next one is for removing hashtags. While hashtags may indicate sentiment, they're removed here for simplicity and to avoid sparse text. The next one is for removing punctuation. This helps focus on the words themselves, although some models may handle punctuation meaningfully. The next one is to remove numbers. In many sentiment analysis cases, numbers don't add much value. The last one is to remove extra spaces. It collapses multiple spaces into one and trims leading and trailing white space. This results in clean and consistent spacing between words. Then return the clean text. Let's apply this function to the original tweet column and creates a new column called clean text, which stores the preprocessed version of each tweet. Now you'll see the clean text, for example. Numbers are removed, text is converted to lowercase, and punctuation marks are eliminated. After all cleaning steps, the processed text is returned for use in further steps like vectorization and model training. 6. Preprocessing. The goal of preprocessing is to convert the clean text and labels into numerical formats that can be used by machine learning models. This involves splitting the dataset, transforming the text into numeric features, and encoding the sentiment labels. First, data split. Before vectorizing the text, we split the dataset into training and testing sets. X contains the clean tweet text. Y contains the sentiment labels. We split 80% of the data into the training set and 20% into the test set. Setting random state ensures reproducibility. We do this before vectorization because we need X text test untouched for the final prediction step. Later, we will compare true sentiment with predicted sentiment with X text test, which is the text data before vectorization like this. Next, vectorization. We convert the training and testing text data into numeric features using TF-IDF, term frequency inverse document frequency. TF-IDF vectorizer transforms words into numerical vectors based on how important a word is in a document relative to the entire dataset. The max features 5,000 inches limits the feature space to the top 5,000 words by importance. The fit transform learns the vocabulary from the training data and transforms it. The transform method applies the same transformation to the test data. The difference between fit transform and transform is that fit transform method learns the pattern from the input data and then transforms the data into numerical features all in one step. It's used only on the training data because this is where the model learns the vocabulary. On the other hand, the transform method only transforms the input data based on what was learned earlier using fit. It does not learn anything new. You use it on the test data to ensure the model processes it the same way as the training data. So using fit transform on the test data would be a mistake because it would introduce information leakage from the test set into the training process. After the vectorization, the output looks like this. The output is in sparse matrix format. Each line follows row index, column index, and value format. The vectorizer has learned a vocabulary of 5,000 words, as set by max features 5,000. Each tweet becomes a 5,000 inches dimensional vector where most values are 0 because a tweet is short. Non-zero values represent words that appear in the tweet, and their value shows how important the word is in that tweet relative to the dataset. For example, words like borders from the tweet probably correspond to some of those column indices. Next, encoding labels. Finally, we convert the target labels from strings to integers using label encoding. Label encoder assigns a unique integer to each class label. For example, negative is 0, neutral is 1, positive is 2. This step is essential because most machine learning models require numeric target values. After preprocessing, you have xtrain and xtest as numeric feature matrices from TF-IDF. You have ytrain and ytest as encoded numeric labels. The data is now fully prepared for model training. 7. Training. The goal of this step is to train a machine learning model using the pre-processed data. The model will learn to recognize patterns in the training data that associate tweet content with sentiment labels. Let's use logistic regression as a model. Logistic regression is a simple but powerful classifier that works well for many text classification problems. Despite its name, it is commonly used for classification tasks, not regression. It finds the best boundary between classes based on the input features TF-IDF values. Max iterations 1,000 inches sets the maximum number of iterations the model will try while optimizing. TF-IDF often results in high-dimensional data, so a higher limit like 1,000 ensures convergence. Then trains the model using xtrain, which is feature vectors for tweets, and ytrain, which is sentiment labels encoded as integers. During training, the model learns which patterns of words are most likely to correspond to each sentiment class. The model is now trained and ready to make predictions on unseen data. It can classify new tweets into positive, negative, or neutral based on their content. 8. Prediction. The goal of this step is to use the trained model to predict the sentiment labels for the unseen test data. These predictions will later be compared with the actual labels to evaluate model performance. The model predict takes the TF-IDF transformed test data and outputs the predicted sentiment labels. These predictions can now be compared to the true labels. At first glance, it seems like the model predicts the label accurately. Let's move on to the evaluation step to measure how well the model performed. 9. Evaluation. The goal of this step is to measure how well the model performed on the test data using common evaluation metrics like accuracy, precision, recall, F1 score, and the confusion matrix. First, accuracy score. Accuracy is the percentage of correct predictions out of all predictions. In this case, the model correctly predicted the sentiment for about 72.5% of the tweets in the test set. This is a good baseline for a 3-class classification task. From the classification report, the model performs reasonably well with balanced metrics across all 3 classes. Let's look at just a few highlights. The model is strong at identifying negative and neutral tweets, but slightly weaker for positive. For example, for negative tweets, 77% of the predictions are correct. Neutral tweets are predicted correctly in 77% of the recalls. For positive tweets, a 65% lower recall means it misses more actual positive tweets. From the confusion matrix, we can know the number of correct and incorrect predictions for each class. This is the visualized confusion matrix. Let's look at some highlights. The model performs best at classifying neutral tweets, correctly predicting 4,624 neutral tweets, but predicted 651 of them as negative and 712 as positive. Positive tweets are the most misclassified, especially as neutral, 1050 times. So the confusion mostly occurs between positive and neutral, suggesting the language used in those classes may be more similar or subtle. So these results suggest that this is a balanced and reasonably effective model, with room for improvement, especially in handling positive versus neutral tweets. 10. Visualization. Let's go over the sample comparison between true sentiment and predicted sentiment. This code creates a new data frame named results that compares the actual sentiment labels to the predicted ones. Xtext test values gives you the original tweet text from the test set. Inverse transform converts the encoded labels back to their original form, like from 0 to negative. The same goes for ypred. It decodes predicted labels. The results sample displays a random sample of 10 rows to visually inspect model performance. Okay, let's check the result. Looks like the model performs well overall, especially for negative and neutral tweets. 8 out of 10 are correct. Most errors come from confusing positive and neutral, which matches the confusion matrix insight. These examples highlight how subtle tone or informal language can challenge the model. That's it for this task. If you want to improve it further, you can focus on boosting recall for positive tweets through more training data or balancing techniques, and exploring other models such as support vector machine, random forest, or fine-tuned BERT. And that's it for today's lesson on this topic. We explored how to analyze the sentiment behind tweets using machine learning. You learned how to clean raw text data, convert it into a format that models can understand, build a sentiment classification model, and evaluate its performance. Working with text data can feel a bit intimidating at first, but you've just taken a big step forward in natural language processing. Sentiment analysis is a valuable skill that combines data science and language understanding, and it opens up a lot of exciting possibilities. Keep experimenting with different models, try new data sets, and watch your confidence grow with each project you build. Okay, thanks for watching today's lesson on Coding Fab. I hope you found these tips useful and feel more confident. Remember, practice makes perfect, so try using these tips in your project. If you enjoyed this video, don't forget to give it a thumbs up, share it with your friends, and subscribe for more Fab coding lessons. Until next time, keep practicing and stay Fab.